Hi everyone, thanks for coming. Thanks for braving the rain. Today we've got Professor Chamkaur Ghag of UCL giving us a talk. The research focuses on certainly the dark matter. Over to you.
Great. Thanks, Alexander, for inviting me. Thanks for coming out. Yeah, it's quite some weather. It's been quite a few years since I've given a talk at University of Cambridge, actually. So yeah, thanks for having me back and for showing up. Yeah, I've spent something like 20 years not finding dark matter. So I'm going to tell you about all these, the latest iteration of us not finding dark matter. That's but you know, in all seriousness, there's a huge international effort out there, right, trying to understand the nature of dark matter. And for us, it's sort of, you know, the particle physics of it. What is this stuff? How's it working? How's it interacting and all that? We'd love to know, but first we'd love to just have it do anything, right? Have it actually interact. So that's what this talk will be about, where we are, where we are in the search for direct dark matter. And by direct dark matter, I mean, you know, there'll be a few ways that we can go about looking for dark matter. We could create it in accelerators at the LHC, which is all well and good. You'd see some missing energy, you know, things smashed together, some particles created. Maybe it was dark matter from the early universe, but maybe not. Maybe you've seen some new early universe particle, but that it's stable on the timescales of our universe would be unclear from the LHC, right? For all we know, you see a missing, you know, some missing mass. It indicates there's a particle there, but as soon as it leaves Geneva, it decays into something else and could it possibly be the dark matter that we know and love, or think is there, at least, if not know as well. The other way to do it would be indirect, right? We could go and look at from the center of the sun to the center of the earth to more like the center of the galaxy, and see if we can spot, you know, dark matter annihilations. If dark matter turns out to be its own antiparticle, most models say it would be, then we'll have annihilations happening. And although we're not very good at finding dark matter, we're pretty good at, you know, picking up positrons and gamma rays and neutrinos and things like that, right? So if it's annihilating, maybe we can see a signal from the center of the galaxy or something like that, some sort of excess. And again, you know, there are issues with that. How do you know that's really the dark matter that you're seeing? How do you know it's not some other background object, et cetera, et cetera? There's lots of fun that can be done there. And then the direct sort of gig is to say, well, all right, we've got dark matter in our galaxy right here, right now, that supposedly is moving through us. If our models, you know, if it's a form of particle, this is going through us all the time. Can we try and catch it? Can we try and have it interact? So our dark matter, if you like, our own galactic dark matter coming through us right now, I want to see that. And that's what we call direct dark matter detection. And that's, so these three sort of prongs that in terms of trying to go after it: accelerator, indirect, and direct. No, you don't want to. Interesting. Okay, so the evidence for dark matter, I'm going to be very, very brief. I'm sure you're all very familiar with this. So you've got the galaxy, you know, rotation curves that would indicate, yeah, if you calculate how the radial velocity of the objects in this galaxy should fall off, it should do this. What we see is this, and so the difference there, that's what we're calling dark matter. But then we've got much more, you know, this not galaxies, but clusters of galaxies almost 100 years ago that were being looked at, and then more from the 70s onwards, individual galaxies, and this year the data keeps pouring in. Then there's things like large-scale structure formation and simulations where you say, okay, I just want to create some galaxy. I want to create some structure in the universe in computer simulations. What do I need? And if you put, you know, the known laws of physics in, which is just gravity, and put some sort of, you know, particle masses in there, and you let it run, evolve this through time, what you'll find is that galaxies will start to form, but then they won't. They'll spin up and break apart. So, you know, some 14 billion years after Big Bang, you don't end up with things like this. So unless you put in some dark matter component, right? Then it starts to work out, and you find, you know, the differences between observation and simulation are not very strong. And then there's things like the bullet cluster, of course, which is, you know, where you've got interacting two clusters of galaxies that come together. And then the gas is all sort of interacting there, and you can see that emitting in the X-ray. But when you gravitationally lens this system, what you'll find is that most of the mass is either side. of the X-ray emission, as if there were clusters of galaxies with lots of dark matter there around them, or in them, through them. And as they've come together, the gas has started interacting, sure, but the stars and the dark matter have just ghosted past. Right? So the masses are now out here. And you can see that if you gravitationally lens the system. And then my own favorite is the cosmic microwave back. Right? So here we've got predictions that came in before data points. Data points come in, they land right on top of this. So sort of understanding of the Lambda CDM model is pretty nice. And what you need for this to work, and again, dark matter. It has to be there early on in the universe for this picture to make sense. So we put all that together, and what are we left with? We have a pie, a sort of universe pie that looks something like this. Dark matter makes up about 27% of everything, and that's about 85% of the matter in the universe, which is a fair bit to not know about. So what could it be? There are things going on out there in the cosmos that indicate that there's something. There's dark matter. Our galaxies are being held together. I'm assuming, how many of you are sort of familiar with dark matter at some form or another? Is anybody? Should I step back a bit and just talk about dark matter? Anybody like me to? If not, all right. There's stuff. There appears to be essentially, we look out into space and then we see things moving around as if there are things with mass there, but we can't see them, and they're having an influence on things that we can see. And that is, the cause of that is what we're calling dark matter. And it makes a few assumptions, that name, right? Dark, all right, it's not really dark, it's transparent, all right, we can forgive that one. Dark just means we don't know what it is. But matter, is it matter? You sure? We don't actually know, right? It's not necessarily matter, but a lot of models out there, lots and lots of theoretical physics over many decades has thrown up lots of candidates for dark matter. And the kicker is this, that it could be anything from masses out here in the sort of 10 to minus 22 EV, even lighter, some of them, all the way up to this kind of stuff, GeV, TeV, and then into solar mass type stuff. And the range here is absolutely ridiculous. So if you want to go and find a particle like this, and the trouble is, I'm assuming you're all astronomers. If I ask astronomers, like, so what one would you most like? Would you like this one or that one? They all work. It's all good. It's like, go do your particle physics. Tell us, whether it's a matcher or a Higgs coupling or this, that, and the other. But as far as the stuff out there is concerned, dark matter, like, it could be any of this. So we say, okay, thank you, astronomers. Let me see what I can do. Like, try and create a net that captures all of this. Very difficult. So what a lot of the effort has been to date has been here in this sort of range. And so this is where weakly interacting massive particles will land as well, or WIMPs. And so that's not to say dark matter must be WIMPs. Doesn't have to be. It doesn't have to be any of this. But WIMPs are a good candidate for us to go after. And where's WIMPs are coming from essentially this idea, or it'll be called a WIMP miracle. It's not so miraculous, but all right, it has this funny name. That if you sort of cook up some beyond the standard model particle physics theories that are going to try and explain lots of other types of stuff, be it vacuum stability to all sorts of different types of beyond the standard model physics. When you start to extend it, a lot of them will have these sort of throwaway particles at the end of it. And so many of these, so for example, the neutralino will come out of supersymmetry, where supersymmetry is trying to sort of deal with some other problems in particle physics. But what it ends up giving you is a stable, massive, weakly interacting particle that will have been around from the start of the universe, would still be here today, and fits the bill for dark matter almost perfectly. And it's not just supersymmetry that does that. There's lots and lots of different models that will throw up this kind of candidate. And they all sort of generically land here in WIMPs. And that's really what I'm going to focus on. And a lot of, here and there, I think to myself, you heard the saying, like, aren't you looking for your keys under the street lamp? And the answer is yeah, because there's light there. So let's look there first. Let's see if, the easy Occam's razor would tell us that this would be so trivial, right? If it's just an extra particle, it's a WIMP. That's it. We can sort of be done with dark matter. Of course, it's never going to be that easy. It could be that, you know, this dark sector where we're looking for some evidence of in terms of, you know, a WIMP or some kind of, you know, dark matter particle. Why should it only be one particle? If you think about the non-dark sector, our sector, we've got plenty of particles. So maybe it's very complex, this whole dark sector. Maybe there's all sorts going on there. But to start with, we'd like to just see something, right? And so we've sort of begun here, but I'm going to talk about some of these other ones coming up here, if there's time at the end of the talk as well. Other candidates, axions, you know, they're very, very well motivated from the strong CP problem. So, you know, do they exist? Are they about? Could they be the dark matter? Unknown answers to all of that. But we're gonna dive into WIMPs for about 20 minutes now. If this stops misbehaving. What are you doing? Okay. So this just, you know, pictorially showing what I was saying earlier. You know, we have a nice sort of the noddiest Feynman diagram you could possibly imagine. Standard model particle, standard model particle in. Magic happens here. Dark matter particles out. Okay, so you can move up this diagram with production in the accelerators, right? Just smash them together, get some dark matter particles out. You won't measure those, but you'll see the missing energy, and you can infer their presence. Or you can go this way, indirect, say annihilation. Again, magic happens here, and some standard model particles out that we can measure. Or we can go the direct route. And so the direct route, if it's a weakly interacting massive particle that you're after, that gives you a way to go about it. What that means is that an atom, you know, a terrestrial atom, if I want to have dark matter, if I want to detect dark matter, there's a chance that I'll have a weak interaction here, which means that there's a chance that I could have a dark matter particle come in and hit the atomic nucleus of an atom, right? So, and that's what direct detection really is. You've got a load of nuclei, and if something were to come in and hit that could be a WIMP. That could be a neutron as well. But if you've made a detector, if there are no neutrons in the environment, and you can prove that, and you still see something, you know, coming and hitting nuclei, and you see a nice annual modulation and all this kind of stuff, and it only hits, you know, one atom and then off it goes again, maybe that's dark matter. So that's what we're trying to search for. We're looking for, we're looking for. I do this in outreach talks, actually. This is an outreach talk, and you're all very smart. But I enjoy this. I enjoy this as a sort of thought experiment. I often say, all right, if we were to hold up our finger and just wait for dark matter particles, right, to come through, what we're looking for is, you know, I've got something like 100 to 200,000 WIMPs going through my finger every single second. They're going at about 500,000 miles an hour. And if one were to hit the nucleus of a single atom, it would give it a recoil that would be about 1,000th of a hair's width. Okay, and it's only going to happen about once every, I don't know, in a finger million years, couple 100,000 years. So this is supremely rare, this interaction that we're looking for that may happen. And if it does happen, it's going to give you a recoil energy of absolutely nothing. I mean, peanuts would be great. This is crumbs of peanuts, right? This is KeV scale at best, energy depositions that we're looking for. So the tiniest energies and the rarest processes. Now, for instance, you know, we're pretty good at low energy. You know, if you say, okay, we need to make something that, you know, can detect a single photon, a single electron. All right, cool, we could get to that. Or we want to build something huge, neutrino detector or something like that. We can do that. The dark matter gig is to combine them both. Right, that's where the challenge is. So, for a couple of decades, we've been maturing a particular technology that uses liquid xenon. It's a liquid xenon time projection chamber. And the reason we use liquid xenon is because it's a wonderful scintillator. If you drop, you know, some energy into xenon, it'll just start scintillating away. It's got a wonderful sort of, you know, it scintillates in the UV. It's, you know, if you've ever been followed by a fancy Mercedes shining this blue sort of lovely light into your rearview mirror, that's xenon in the lamp. Okay, so it's that stuff. And if you extract this from the atmosphere and you have enough of it, then you can make yourself a dark matter detector. So I'm going to go through how this works, but essentially, dark matter particle comes in, and it would interact with the nucleus of an atom. You'd have some light, some photons, scintillation photons liberated. Dark matter particle's gone again. This is just like It's like playing snooker or pool, right? You're not catching the WIMP or anything, it's just hitting and off it goes. So that's gone. You get a load of photons, and you want to catch those photons. You want to, you want to detect them. So you want to, if I've got a bucket of liquid xenon, I want photosensors, top and bottom. So photomultiplier tubes is what we tend to use, so that we can catch this light. And if we were really, really rich, we'd have photosensors up and down the sides as well. We're not. We just use reflective PTFE. It's incredibly, I think it's 99 more, 99.99% reflective in this sort of wavelength. But it's essentially Teflon, actually, it's just white Teflon. So if you imagine a barrel of white Teflon, about 1.5 meters high, and then about 250 photosensors as one end cap, another 250 at the top end cap. And then you want to put the whole thing, this whole sort of, detector, into a thermos flask, because you need to keep this cold. Xenon is a gas in the atmosphere. For this to work, you need to liquefy it, which means you have to have it about minus 110 degrees Celsius. So you want it in a thermos flask. And it literally is just a double-walled thermos flask. Like we use titanium, and you're pretty much good to go. You need to keep that xenon purified. You need to keep it cold. That's huge amounts of infrastructure. It's, for the detector about the size of, from here up to the ceiling, the rest of this room would be filled up with everything else that's required to power it and keep it clean, keep it pure, and everything. But coming back into the inside of the detector, it's not quite a bucket of xenon. It's not quite as simple as that. We're going to put some electric grids, some potentials across here and at the top here, so that we can have an applied electric field across the xenon. Now what's going to happen is that when we have a particle come in and hit our xenon, we'll get a flash of light. Why are we getting the flash of light? We're getting the flash of light because you've got some energy come in, you've hit this atom, it's gone and smashed into others, they've become ionized, and you've got lots of charges around. Eventually they're going to recombine around the track, where the recoils happen. And when they recombine, they're excited, they need to shed that energy, right? So they're going to decay, or they're going to kick off a photon. So that's where these photons are coming from. But if I have an electric field across this, let's rewind the story and look what happens now. I have a dark matter particle come in, hit my nucleus smashes into other xenon atoms. Either side of this track, I've now got ions and electrons. They're going to want to recombine and give me that flash of light. This time I've got an electric field across them. So some of those electrons, they don't get to recombine because I pull them away into the up to the top of the detector. Once they get, so some of them still combine, and I still get this flash, some don't, and then up they go up here. Once they get to the top of the detector, I haven't quite filled it up with liquid. There's a gaseous layer there. And once they get into the gas, we can have secondary scintillation, electroluminescence, and you can generate a massive great flash of light there. We can control that flash. So here we're detecting, this is a real sort of waveform. This is a few photons. Okay, so the detector is sensitive to a single photon. We're also sensitive to a single electron. A single electron going up there would give us another 50 photons or so. And so this comes from just 1 or 2 photons, 1 or 2 electrons, sorry. So you can't really do much better than that. It's sort of single quanta counting here. So you get a first flash when it comes in, a prompt scintillation flash. Then as the electrons drift up and they make their way into this gaseous layer, we get a second flash of light. And these 2 flashes of light, they're very important for us for many reasons. One, particle discrimination. So what we're showing here is essentially the ratio of that secondary flash to that primary flash against the size of the primary flash. You can take that as energy if you like. And what you'll find is that if I've got a dark matter particle come in and hits my nucleus, the nucleus it's going to create a very dense track as it smashes through the rest of the atoms. And so the probability of recombination is quite high. It's all quite localized. And so you get quite a large or relatively large S1 primary flash. That means that I've sort of suppressed the number of electrons that can be liberated because we've caught most of them. So you get a smaller S2. So high S1, small S2 is nuclear recoil light. Be that WIMP, be that neutrons, they would land here. Anything else, if I have a gamma ray coming in, the gamma ray is going to come in and hit the electron. The electron is just going to have this diffuse fuzzy track, which will allow us to, which won't give us much of an S1, but will give us a much stronger S2, because there's, essentially you're outside of the Onsager radius. So now I can see that most of my electromagnetic backgrounds, which is pretty much all of our backgrounds, land up here. So there's a nice sort of separation between what's going on up here and what's going on over here. They might not look that great in terms of separation, but what we're dealing with something like 99.5% discrimination. So only about 1 in several hundred of these is going to leak down into this region and look like it might be a WIMP. But then we can profile it, see where it happened, and so forth. So is that clear? That one of the important things is discrimination. You want to tell the difference between something hitting the nucleus and an orbital electron or something like that. That's really important because there's an experiment out in Italy called DARMA. So anyone heard of DARMA? Okay, well, it's an experiment out in Italy, and it uses sodium iodide. It's a very, very simple experiment. Sodium iodide, photomultiplier tubes, they see stuff, it pings away, and they see it come up in the summer, down in the winter, and it looks like it's an annual modulation, as if this were dark matter. The trouble is they can't tell us whether what they're seeing is electromagnetic radiation, whether it's hitting electrons or it's hitting nuclei or what it's doing. There's no discrimination, which makes it very, very hard to tell that this is dark matter. Plus, it's not dark matter, it's background, they just won't accept it. Anyway, we've been past, where I'll qualify that actually. This is where Dharma lives. Let's say their signal region is here. We are now orders and orders and orders of magnitude below them. We have detectors so much more sensitive than that ever was, and we don't see anything. We kind of know where they're potentially going wrong as well. But that's maybe you can ask some questions at the end if we've got time about that. So discrimination is one thing. The other thing is that we can have 3D vertex reconstruction. That initial flash of light sets a sort of T0, start the clock, and then I see something else happen up here. If that time was short, well, then this event was quite close to the surface, right, of the liquid. And if it's deep, then it would take longer. So that time gives us our Z component. And then you remember that secondary flash at the top, we can control. We can amp up the field there and make it as large or small as we like. And so that gives us great XY resolution in that plane. So with that, we get 3D reconstruction of our vertex. And that allows us to play some games which says, look, we only really want to look in the central part of our detector. Because xenon itself is actually very, very, it's very good as a self-shield. It's quite dense. It's sort of 3 grams per centimeter cube, which means that gamma rays coming from the outside get stopped by the xenon itself. So ideally, if you want to make a dark matter detector, you want a floating ball of xenon that magically tells you psychically that something's hit it. Failing that, have some light sensors, that's all good, but make sure that they are incredibly clean in terms of no radiation coming off these things. And because you can't just float a ball of xenon, you're going to have it in some other stuff, right? So the point is the xenon is held with stuff. The stuff, no matter how clean we try and make it, has uranium, thorium, potassium, all sorts of gunk in it that comes out. But it comes out from the edges, right? The edges of the volume. And if you can tell it's coming from the edges, you can just clear it away. And then you can also build other detectors. You can get detectors and detectors and detectors in this sort of onion ring, onion shell, Russian doll type configuration. And you can say, look, if something hits my xenon, but also hits a detector out here in coincidence, that's not WIMP, right? So forget it. We can kill that. So we can take our, we can end up with something like just a single background count in 3 years of run. Right? That's the sort of targets that we're aiming for. These things have to be incredibly, incredibly clean. And I'll come to that in a second. So that's a generic liquid xenon TPC. We've been working on those, as I say, for a couple of decades. About 10, 12 years ago, they sort of went past the leading technologies at the time. So previously it was crystals and things like that. And as xenon, as a liquid noble gases were sort of being matured for dark matter detectors, the obvious fact that you can grow them as a volume took over, right? If you want to double the mass of a very sophisticated crystal-based dark matter detector, you need 2 of them, right? There's not much more you can do about this, and all the electronics and all the complexity that comes with it. With a bucket of xenon, make the bucket a bit bigger, and you get some freebies for that. As you get larger, you're shielding more and more of that radiation from the outside. So the inner part of the detector is getting cleaner, but you're accruing more and more mass and more exposure. So long as you can still apply an electric field across this thing, you're good, and you can keep going. So the LUX-ZEPLIN collaboration is one of the collaborations that uses liquid xenon time projection chambers. It's formed of the LUX collaboration previously of ZEPLIN. ZEPLIN was the collaboration that pioneered this technique. The first liquid xenon TPC to run as a dark matter detector, bearing in mind that for the last 10 years, every single world-leading dark matter detector has been a liquid xenon TPC. The first one was at Bolby Mine, up here in England. And it was the Zeppelin collaboration that was doing this. They ran a series of detectors. And then LUX was an American, a US collaboration. And eventually we came together to make LUX-ZEPLIN. The UK program sort of stopped. LUX wanted to get larger. We sort of joined, pulled our resources, and here we are now, some 250 scientists. So where we are is a mile under the Black Hills of South Dakota. So remember, we're looking for incredibly rare interactions. So rare that, you know, for a ton, or actually, if I had a 7-ton detector, 7 tons of liquid xenon, and I ran it for something like, you know, a month or something like that, we would not see dark matter. That's the sort of level that we're at now. So it's an incredibly rare process, and I'll get into more. I'm aware that was quite a garbled sentence, but I'll come to that in a second. What I'm trying to get at is that it's a rare process. We're looking for something incredibly rare. What isn't rare is Sky TV, signals from everything, cosmic rays, everything else. Right. So the very first thing you want to do is get your detector away from all kinds of radiation like that. Get it away from the surface in particular. Get it away from the cosmic ray and the muons. It can activate components. It's a massive, massive rate. So you can drop the rate of muons by, you know, 1 million or so by going a kilometer underground, just like that. So get underground. In the Black Hills, there's a mine called the Sanford Underground Research Facility. It used to be a gold mine. This was, I think, the biggest gold mine in the States or world. But they're done with the gold. It was turned into a science laboratory. And this is also where DUNE is being built. And if you heard of DUNE, this is the big neutrino experiment. So that's where this will be going. Okay, so the detector itself looks like this. This is LUX-ZEPLIN. So, you know, inside there, this will be the xenon. These are our banks of photomultiplier tubes. You can see them here. They're the eyes of the detector, sensitive to single photons. And then inside there will be the cathodes, and we apply grids and some anodes and extraction grids up here. And the whole thing is built from incredibly pure materials. And I'll briefly go into that. Actually, I'll spend a minute talking about how pure. So we spent 5 years looking for and screening about 2,000 different bits and bobs, from the titanium, this is going to go in, to every photomultiplier, to every gram of material inside the photomultiplier, we screened. So we said, give us the material before you make the photomultipliers, please. And we screen them for gamma rays, neutrons, everything. We measure what's in there. And then we say, sorry, you can't use that material. Give us the next one. No, yep, you can use that one. And so all the components are made from low background components. Let's say a couple thousand materials screened. Up at we mine a lot of it over the course of 5 years to select the materials that we're going to build the experiment from every single watcher, everything we see. The reason for that is because you remember that one background neutron event in 1,000 days. That's what we're trying to get at. We're only looking for a few WIMPs, right? And if we had a few background events, well, then it's game over. So this has to be incredibly, incredibly clean. In terms of radio purity. And then once you've got all the components built, you built the detector from very, very low radioactivity materials, then you have to piece it all together, right? You got to plug all the photomultiplier tubes in, get all the cabling, do all this kind of stuff, actually assemble the detector. Now here, when you're trying to assemble a detector, if we were to open up the detector, and just look at its surface area, like our intestines, it's like, it's kilometers squared. This is a huge, huge, huge surface area, all the cables and everything. Over that entire surface area, if we cannot afford to have more than 1 gram of dust integrated. So total 1 gram. If we have 2 grams, we may have blown $100 million experiment. If we got 3 grams, it's like, crap, let's all just blow home. So it's incredibly, incredibly pure. The reason for that is that dust is actually, it's pretty bad for radon. Lots of radon comes out of this stuff. So we don't like radon, we don't like potassium. Don't come near this detector with bananas or walnuts or anything like that. Uranium, thorium, you don't want any of that kind of junk near it either. So it's got to be incredibly, incredibly pure and clean. So the pre-construction phase of it is super important. And then the assembly part of it is as well. You got to build it clean, know you've built it clean, be able to prove that you built it clean, all of that. So this is a little schematic of what it looks like then. So we've got LZ is the main sort of thing here. As I said, it's inside a thermos flask, a titanium one. I was heavily involved in all the radio assays and backgrounds and stuff and everything. And the titanium was a really sort of fun / interesting story where we really wanted to use titanium because it's typically very low background, but the folk that sort of process titanium, a lot of it comes from Ukraine and Russia, but then it will get processed in places like Las Vegas and things like that. And there we were. So I was saying, would you mind stopping your multi-million-dollar processes, every day, just interrupt it for a moment and not do this and do it this way? And to our sort of joy, they said, yes, sure, we'll help science. We want to help you find dark matter. And so we were able to work with them and say, look, if you actually don't do this, and you do that, and you do this, and you do that, we could get what we need here, because we screened everything from them. We said, give us your raw pellets, give us this, give us that, give us that, give us that. We screened it all to figure out where the contamination could enter and ask them to change it. And so we had to do that with quite a lot of the components in it. And my wife used to ask me, like, why don't you just go buy this stuff? Like, it doesn't exist, dude. You literally have to go and make this stuff up. So outside the liquid xenon TPC, we have between the thermos flask, the sort of metal part of it, and the PTFE, there's a bit of xenon there, which we call our skin. So anything happening in that skin region, like a prompt gamma ray, would interact in the xenon and in the skin xenon, so we can reject it. But then we also have an outer detector that is like 20 tons of liquid scintillator that is great for neutrons. So any neutrons that do, so let's say a neutron comes off the PMT, hits our detector, it hits the xenon and then bounces on the xenon again, we can get rid of that. That's obviously not a WIMP, and that's a neutron. But if it does something like hits it here, and then we're to leave, now we're in trouble, because that's a single scatter nuclear recall. Right? That's what we're looking for. But a neutron won't make it out of this thing. This is a good tens of centimeters of liquid scintillator. So it ends up getting captured with a big splash of gamma rays that you can detect. Then outside of that, we've got water, a water tank, and then outside of that, we've got the minor block of the Black Hills. And so that's sort of how the detector is sort of stacked up. So this is starting of the detector. LZ is already in there now, and they're getting the water tank. Sorry, the outer detector, the scintillator, going. This is the one of the cryostats sort of outside. And then finally, if you were inside that water tank, you'd be dead. You'd be floating around and you'd be in good company. You'd have all of this stuff around you. So this is all submerged, right, in water now, and has been for a good year or so. But it's all, if you're a photon in that detector, you should be seeing only active photocathode area where you can detect it, or a reflective surface. Okay, so now just a little bit, how am I doing for time? All right. A little bit on the xenon physics. So it's actually I can go quite quickly. The energy response of liquid xenon is quite magical actually. It's essentially saying that anything that doesn't go into the light signal will end up going into the charge signal. So you can end up having a really nice combined energy scale. If I can figure out the energy of my event from the light, or I can figure it out from the charge. And the ratio of them is going to tell me something about the interacting species. But in terms of the energies, this is great. It means that if I sort of plot, if I put some radioactive sources in front of the detector and I look at the secondary charge against the secondary signal against the primary signal, I see these lovely sort of straight contours. I can identify the peaks really easy. Which means that we've got some excellent resolution in this detector. And then some of the quantities that we want to maximize are these ones. The light gain just means if I'm a photon in the detector, how likely are we to catch it? And so it's only about 11%, in fact, right? Because I mean, the photosensors themselves are only 30% efficient, so you get massive losses all over the place. But all right, as long as this is above about 8% or so, we're good. And then the second one is just our own amplification in the gas region. And so then you say, okay, we built LZ. How well does it actually work? Yeah, this is that discrimination plot again, and this is real calibration data this time. And what we do is we calibrate our electron recall band with tritium. And so we can create tritiated methane, which we can pump into the detector. It disperses all around. but then we can get to it. We can sort of get it, we can flush it back out again. So the xenon is continuously being purified, and it's going through a gettering system of purification, and the tritiated methane gets trapped in there as well, so we can remove it very easily. Or you wouldn't want tritium stuck in there. But it allows us to calibrate our band very nicely, because we know this is a beautifully clean beta emitter. So we know, what the energy spectrum of this thing should be, and then we can figure out our efficiencies. What are we not seeing down at low energies, for example. And then we can put neutron sources in front of it as well. This one was a deuterium fusion neutron generator that exposes a detector to neutrons, and then we can see where our neutrons are going to land. So we can check that. All right, we kind of know where our signal should be. Then get all that tritium out of there, and take the neutron source away, close it all up, and just start running, and see what you see. But before you do that, or when you start doing that, you need to really make sure that you understand your backgrounds. So remember, it's the reason we did all that cleaning and screening and making sure that the detector is very clean is, one, to make sure that our sort of overall background rate is low enough such that we'll be able to see a dark matter signal on top of it. Okay, so it's just as simple as that. But there's a complexity in the background modeling. We need to make sure that if we do see something, a couple of events or a peak or something that looks like some new physics, we can only really give that, we can only ascribe statistical confidence to anything we're seeing against the background model. We have to know what is there in the absence of dark matter very, very well. And that's really what the screening secondary goal is. Every time we're putting a component, I want to know how much uranium and thorium is in my titanium or anything. The reason is because I then need to run a whole ton of Monte Carlos to generate all of this stuff, to see exactly what we're going to see in our detector in the absence of WIMPs. Okay, and then we're looking for something on top of it. So the background model is everything. If anybody says, hey, we found dark matter, just say, show me your background model, and then go to town ripping it apart, because probably the background model's wrong. Okay, extraordinary claims and all that kind of jazz will need extraordinary evidence, and it's all the background model. So we can extend our background model out to higher energies. This was quite fun. In LZ, we found that we also had sort of great energy resolution and sort of background understanding at quite high energies, typically dark matter detectors. So the WIMPs are expected, here. But we're able to sort of map and see everything. And we need to do this because we need to know what's leaking into this. So we want to map all of this really very well. And you can see some areas where we're not doing quite so well, especially here and places like that. But in terms of what that implies to the number of counts over here, we're getting into 0.001 or something like that. As long as the uncertainty once you get into WIMP region is low, that's good. But it does allow us to do some funky neutrino physics up here as well. So it turns out LZ is going to be quite sensitive to neutrino stubble beta decay, which is quite cool, right? Because you'll be able to get neutrino stubble beta decay and dark matter from the same type of experiment. Okay, so this is more on background. You can learn or read more about them here. In terms of what we were seeing and everything, but in terms of total expected nuclear recall counts in our first run, we only expected something like 0.15, so hardly anything. The number of electron recall counts we expected in our first run was 276. So when I mean first run, back in 2022, was it? Must have been. Towards the end of 2022, we had after 10 years of pre-construction, screening, construction, assembly, get the whole thing. So you have to get this detector from the surface lab where we put it together. Those pictures I showed you were on the surface. Then we have to move it down a mine shaft, then get it into the lab, and then get it all kitted out and everything. All of that was almost bang on 10 years that took. And then after that, we calibrated. We took that tritium and DD data. We had a look at our backgrounds, and then we said, okay, let's just get running now. We need to run this thing and take all the sources away and see how sensitive it actually is. And we only ran for about 60 days. The sensitivity projection, LZ will sort of bottom out after about 1,000 days in terms of nuclear recall events. So 60 days was just 6% of our planned exposure. But in those 60 days, and I'll come to the results of that in a minute, because could have seen WIMPs even in those 60, unlikely, but could have. But it did show us something. We saw 276 events in those 60 days. That's equivalent to about 1 event per day per ton in our detector. what that means is that we're talking about the most radio pure volume of space anywhere on or in Earth. There is nowhere more radio quiet than this, the center of this detector, in looking for nuclear recoils, right? And so that's really what we're trying to get at. We want to create an observatory, if you like, that can look for electroweak physics, as low mass to as high mass as we can go, with as much sensitivity as we can get. And then maybe there's WIMPs, maybe there's not WIMPs, maybe there's other new physics, maybe there's neutrinos, beta decay. But that's kind of the game. But the point is the construction, the cleanliness, all that sort of stuff is to make sure that we are incredibly clean, which we managed to do. This is then looking at efficiencies. It just shows you, after about, from about a few kV or so, we get to sort of 50% efficiency, which is good for us. Dark matter particles are going to come in like this. We'll have an exponential sort of low energy form. And so we want this efficiency to be as high as we possibly can. Right? Ideally, we want it as 1 all the way up to 0, but that's not possible. And the reason it's not possible, where we're losing efficiency, the first one will be this S1 threshold. So you can see the trigger threshold is pretty good, right? We're triggering on single electrons, we catch everything. But then we lose a massive load of low energy sensitivity in going from this curve to that curve. And the reason for that is that we need to impose a minimum threshold on what we're calling an S1, a primary scintillation flash. What we say is that we need to see a photon in at least 3 photomultiplier tubes within a coincidence window. Any less than that, it's likely to be accidental, just accidental pile up. These photomultiplier tubes have like a background rate that can be hundreds of hertz. So they're kicking off single photons, single electrons all the time. And so, you need to have a multiplicity there to knock that down. Anyway, it's plenty good enough for what we need to do here in terms of look for WIMPs. So these are the results. This was us running after 60 days. We saw this, remember, is the electron recall band. And we see lots of events there. We can sort of draw contours and explain what some of these are. And then we saw some, there's some leakage sort of stuff coming down here, but in the main sort of WIMP region, there's nothing there. And then you can look at where these leakage events are. These are always suspicious for us, things that are leaking down a bit, quite far down into here. Our models predict that, but still we don't like it. And then we can look at what the likelihood of these events are and where they land in the detector. So if the WIMP should be uniformly distributed in this phase space. You can see that some of these are sort of had a little bit of a clustering down here, but no WIMPs, no dark matter. So we ran this through a profile likelihood ratio-based statistical inference and found that we had surpassed the previous world's most sensitive dark matter detector, which was lovely for us. So the way I sort of think about this is that we built this thing, we took it around the block for a spin, and we broke the land speed record, right? It's just like, cool, all right? But this was unblinded. We did a lot of bias mitigation in our analysis and everything, but this was really an engineering one. This is us saying, does our purification system work? Does our high voltage hold? Are our light systems working? Is it all good? And so although we were very rigorous with our analysis, we didn't blind our region of interest. So it's sort of a quickish run. But now what it means is that we are entering phase space that has never been explored, right? So I'm going to pause just for a minute and explain what I mean by this. Actually, I should explain this curve as well. So this is the WIMP nucleon cross section. This is the interaction probability. So the deeper you go into this, the deeper you're going into electroweak physics, right? If you like. And then here's the WIMP mass. We know neither this nor this. What we'd like to do is just draw a star somewhere, right? Saying, okay, we see something that has an energy spectrum, a profile that tells us the mass is whatever, let's say 100 GeV, and the rate of scattering is here. So there we go. We're done with dark matter. That's WIMPs. Let's move on to something else. Go have fun with dark energy or something. But alas, we don't see anything like that. These are the LUX results from 2017, and then came xenon 1 ton. And then there was an experiment called Pandarex in China in 2021. And then when we put our curve out from just 60 days, we've gone past one because it's a bigger detector and it's more sensitive than all of these ones were before. And so the relevance of this, other than to say that, hey, we're the best at not finding dark matter, is that when experiments are typically run, they've got down to some cross-section, right? They've said, all right, we've searched down to here, dark matter does not live up here. But that's all we can say. We're done. Experiment is dead. We don't have enough sensitivity. Our backgrounds are too high for us to go any further now. So that's the end of it. And then we'll come and say, yeah, experiment comes here. Then comes another experiment and says, well, we're catching up, we're catching up, we're catching up. Oh, we beat you. We're the world's best now. And that's the end of our experiment. And then comes another one. Well, it's been kind of boring. We're just sort of inching in front of each other. What the state we're in now is that we've gone past all the others in just 60 days, and we're going to run for 1,000 days. So we've got all of this. So there's no other experiment that can sort of cover that phase space on the timescale that LZ is going to do it, provided it all, carries on working and does its thing. So we're really into discovery territory, as I like to think of it, right? So every day that LZ is now running, and it is running again now. So now we've got it blinded, we've got data salted, we add sort of fake events into our data, so that we can have proper bias mitigation controls in our analysis. But the key thing here, again, and I'm banging about it, is that we are exploring completely unexplored, uncharted electroweak parameter space. Right here, the chances of you finding dark matter from 60 days, given that this experiment already ran, are very small. Right? Chances of them missing it and us finding it, there's no dark matter here, right, in 60 days. But in a couple of 100 days or 1,000 days, we could actually have WIMPs. And so there's a lot of lots of models and things that talk about more dark matter that will be further down, etc., etc. But we're now into an exciting time. Genuine discovery potential, and it's been many years in the making, and with a discovery potential where we're actually crossing into some really interesting parameter space. So we've known for a long time that ideally to get into be it supersymmetry or be it some of these other models, a few ton scale dark matter detector is really what you want. And now we're there, and it's taken a long time, from a few kilograms all the way up to the 7 tons in LZ. So as I said, it can also do lots of other physics though, because it's it's an observatory of sorts. It's sort of physics agnostic, incredibly radio quiet, incredibly sensitive. Let's see what the universe throws up. But it's got xenon 136. Natural xenon contains xenon 136, which is a neutrino double beats decay phosphate. And here you can see this is just showing sort of dedicated experiments that are only neutrino double beats. And then here you can see where sort of LZ could be just as it is. And then if we were to enrich the xenon, it's dark here, which is really kind of cool. It does, this is solar axions and things like that. So there's lots of other physics that it can get on with here. And then in the last few minutes, I just want to talk about what happens next. So LZ, I say, we're not done. We've only just begun actually, and now we're into real sort of blinded science running, and lots of work to be done here. There's also something I should mention actually is boron-8 solar neutrinos. So this one should be exciting. If I go back. Here, there's this thing. So previous experiments have not come across this. They've not been sensitive enough to actually see boron-8 neutrinos. What this is neutrinos from the sun coherently, elastically scattering off of the nucleus. Right? So this is coherent elastic neutrino nucleus scattering, which means you're getting a nuclear recoil. This time off of neutrinos, but it's a nuclear recoil. So that looks just like a WIMP to us. And so boron-8 signal is going to look like it were, say, an 8 GeV WIMP. We won't be able to tell the difference, except that, we've got rates and all that kind of stuff. So, but what is nice about this is that up to now, dark matter detector after dark matter detector has been telling you, haven't seen anything, haven't seen anything, haven't seen anything, haven't seen anything. Are we sure they've been on? Was it power, right? Can you show us anything? Well, now we can. We can perform the world's first astrophysical measurement of coherent neutrino nucleus scattering. It's only been measured once, a standard model predicted process. It's been measured once by the coherent collaboration, who had a dedicated experiment for this, and they used reactive neutrinos. But here we can do it off the sun, and we can measure it in a flavor brine process and get lots of interesting physics out of this. But the point is, even if there's no WIMPs, we should be able to prove that we would have seen WIMPs had they been there by showing you that we will see boron-8. So that will be quite a major milestone for us once we do that. Okay, so what's next? Next would be, actually, if I come back here. So here we see the LZ results, and LZ will get down to about here, 10 to the minus 48 after a few more years. But we will come across something quite interesting soon. Down here, we'll come to what's called the neutrino floor. This is where, so the boron 8 neutrinos are going to give us coherent elastic scattering off of nuclei. But once you get down to a cross section of about 10 to the minus 49, now we'll have atmospheric neutrinos and diffuse supernova neutrinos doing it as well. And that's going to cover the entire energy range. So it's not just like, these things have ruined the low mass search. Now you're done. You can't do WIMP searches with this kind of technology anymore. Is that a problem? I don't think so. And good to hear what your thing. But yeah, 10 to the minus 49. If you haven't seen WIMPs by then, this WIMP miracle, the fact that, if you were to, dark matter particles generated in the early universe, annihilating with a weak interaction cross-section gives us an abundance of pretty much what we see now, right? Well, that's nice. Dark matter must be WIMPs. Trouble is, we're now into not so weak. Now we're into kind of super weak cross-sections. Now we might have to start fine-tuning, right? If you found it up here or something like this, then okay, sure. The further you start going down and down into this, it's just like, well, that WIMP miracle doesn't seem so miraculous anymore, right? So there's a lot of push. There's still, what we really need to do is get down to this point. At that point, we've pretty much exhausted, or I say exhausted, it's not a linear scale. We've got lots of models that sort of peak and will start to appear right in this region as we cover them with LZ and then we cover them with whatever comes next. But the point I'm trying to get at is that there's only an order of magnitude of phase space left after LZ is done. To me, that means there's one last detector, and that last detector will either confirm a WIMP discovery that LZ has made and give you a high stats confirmation, or it will make the first discovery itself, or it will kill WIMPs for good. That's the end of it. Let's be done with them and let's look at other candidates. Because unless you start getting directionality or start getting other things, it's going to be very, very hard to go past a neutrino floor. And for me, why should we? The motivation for WIMP starts to drop quite a bit there as well. Unless, we start seeing things there, of course. But the point is, we still need one more. I don't know if have you seen the little meme going around of the LHC collider, the FCC? Just one more, bro. Just give me one more. That's basically what's happening. But we've got. No, I was going to try and backtrack. Now, that is what's going on here. So we need one more, and the last one would be something like 7 to 10 times larger than LZ, but it would cover all of that phase space, and we could be done with this. The thing is, though, it would also have world-leading sensitivity for neutrino double beta decay. It wouldn't just be comparable to dedicated experiments; it would be kind of better than them. And so in the UK and actually internationally, the program for using germanium and some other target, Legend is an experiment that maybe some of you have heard of, that is sort of the front runner in neutrino double beta decay plan. But if you had another target like xenon, provide confirmation and do it with an isotope, that's really what you want to try and get at the sort of the matrix elements in nuclear physics of what's going on. So we've been working on this generation 3 detector for a while, doing R&D. This is where the neutrino floor is, this kind of stuff here. This is sort of where you get one of them. LZ gets down to here. So you've got another order of magnitude that get you sort of down to this point, so that we could definitively say something about WIMPs and dark matter. Can we do it? Is this bonkers? Yeah. If you draw a line through that, you can see that we've been scaling really well. You'll find lots of dark matter experiments that will say, hey, we're going to build this experiment and we're going to go from, this 1 kilogram R&D thing to 100 million tons because we're great. It's like, no, you're not. Because this was a lot of pain, Every time you went past into new territory, you found new backgrounds that you'd never thought of, because why would you have thought of them? Right? But hopefully we can get down to this. And towards that end, we have, so some of the LZ is sort of competing with another experiment that's very, very similar. It's liquid xenon TPC as well, in Gran Sasso in Italy, called xenon n-ton. And between sort of LUX-ZEPLIN and Panda X, are sort of the main liquid xenon collaborations. It's all we all know each other. We were all working together at some point or another. Some split and went over here, and some joined and went over there, and so forth. But for the next one, XLDD, this final experiment, I think, we've all come together. So this is the xenon experiment, LZ, and then Darwin, which is sort of the evolution of the xenon experiment. And so this is on 600 experiments, 600 scientists coming together to make this thing. And the article that I linked there was just show you sort of, you know, everything that this thing will be able to do. It's quite incredible. And again, it's because as you get larger and larger, the backgrounds in your in the center are getting lower and lower. So provided you can keep your, you know, things like radon that disperse all over the place, keep that down, make sure you can still apply an electric field, have good light yield and so forth, you get much more physics. And then the last thing I want to mention on this is that we could be seeing XLZD in the UK. So this is a, I don't know who may be listening to this. I hope, you know, politicians and things like that aren't, but this is a post-Brexit type situation, right? Where we have Brexit and we find that, that was dumb. And we've lost lots of stuff. We've lost money, we've lost people, we've lost everything. But, you know, government being what it is, says, it doesn't matter because we're going to pump a load of money into becoming a super science nation and things like that. And they're actually thinking and talking this way, right? Lots of money coming in for quantum sensors and doing all sorts of things like that. And so the UK is trying to figure out what it's going to be. And one of the things it likes to talk about being is a science powerhouse, right? The trouble is we don't have a lot big major international kind of experiments here in the UK. And XLZD will be a big one. This is, you know, we'll have Italy, Japan, Snow Lab, Canada, the US. Everybody's going to be competing to host this experiment, to have it in their country. The Bowlby line, remember I told you this is where the first xenon experiment happened. It'd be really cool if we could have the last one here as well. And there's a huge amount of high-level support. So from government all the way down through UKRI and STFC and everyone, everybody would love to see this happen. And it would be pretty incredible. We're also doing some, I mentioned sustainability, because we're also thinking about how we build this thing. You know, given climate change and what's going on, how can we, you know, we're sort of committed to, if this were to come to Bowlby, then the Bowlby lab itself requires a big expansion. And we want to be sure that that would be carbon neutral in operations. And similarly, the experiment, XLZD, we want to be sure that there would be carbon neutral in operations. Because frankly, you know, I always use this picture as my title slide, but I love it because, you know, looking out there is all well and good, but you're still needing on the Earth. Right? If you don't have a planet, we're not going to do science. So it's all well and good talking about FCCs and all that kind of stuff in 2070 and 2060, but I'm not sure if the world is actually, or physicists are actually thinking about the state of the world in 2050 and 2060. There isn't. Right, I'll move on. Bowlby, what we're doing here is one of the things we'd like to do over the last sort of decade or so. We have built up a suite for how you actually go about screening materials. So if I wanted to use this paperclip in LZ or XLZD, I would need to first pop it in this thing. This is a germanium detector, and I'd screen all the gamma rays coming off of it. And I'd figure out how much uranium, thorium, potassium, cobalt there is. Then I would need to pop it in this thing, right? Inductively coupled plasma mass spectrometer. With that, I can measure directly how many uranium and thorium atoms there are in there, which I need to figure out my neutrons. And there's more. There's radon. I need to figure out how much radon is emanating off of this. Radon is an absolute shit. We don't like it at all. But it's very, very hard to measure. And then we need to know how much is, you know, what's the surface contamination on this that isn't intrinsic to it, but it's just landed on it, that is stuck or implanted into it. And for that, we need these things. And we've put together the whole suite, everything that you need to measure all this stuff. What we used to do was I'd measure this at Bowlby with germanium and then have to send it over there to UCL to do ICP-MS and send it to, you know, America to do this stuff. Each time we've got to bag it, tag it, all that kind of stuff. And it just adds to systematics in your background model. Now at Bowlby, we've got everything in one place so that we can build, screen, do the whole kit caboodle. So it could be that, you know, we will have the definitive direct dark matter experiment in the UK. And we'll find out in 2025. That's when the siting decision will happen as to which lab it's going to go to. As I say, the UK is really, really on board with this, which is really good, also kind of terrifying. You think, all right, we're going to be hosting this massive thing. We're going to have to invest in our infrastructure, is my point. That's why it's terrifying. We'll have to invest in like national labs and all that kind of stuff, right? We'll have to make sure that we're really on point and can lead and drive this thing. But okay, last minute, if I may. Do I have time? Yeah. It may not be WIMPs. What else could it be? So something that we've started playing with, or I started playing with at UCL with Peter Barker, a colleague in our atomic and molecular physics group, is this levitated nanospheres. So this is sort of lands into the whole world. So there's lots of sort of what are being called quantum sensor experiments that are trying to look at this stuff. The difference is, do you remember I showed you the energy, the efficiency loss in going from when LZ triggers to then the fact that it needs a coincidence of 3. That coincidence of 3 imposes then a minimum energy transfer, right? It's got to at least have produced enough energy to give me 3 photons. That gives you a WIMP mass cutoff, effectively. I'm not sensitive to anything less than, say, 5 GeV also. But what about this thing? This thing is a 100 nanometer silicon bead, optomechanically levitated. It's basically a ridiculous force sensor. But more than that, it's direction. If something, I can tell what hit it and from what angle and where it's kind of gone to. It's really, really cool. And so Peter Barker and his team in the AMOC group at UCL have been working with these things. We got together and got some funding to try and do an experiment where we were going after a particular type of dark matter called self-interacting dark matter. It's a bit of a weird niche model, to be honest. You can say 7 tons of xenon hasn't seen anything. Why is your 100 nanometer bead going to see something? The reason is because there are some weird models like self-interacting dark matter where essentially it clumps, the dark matter clumps. And so you can have a sort of coherent effect where you can get good sensitivity from these and go after other models that are not WIMPs. That's the point here. And you go after incredibly low energies. And so if you're interested in this, we've just put out a paper on what you can do with these kinds of things. And we are running this. I'll skip this. As actually, well, that's the one we're going. It's just another way of showing that same part. Dark matter could be anything from all this to all that. And what we're sort of looking at the moment is this stuff. So WIMPs is LZ territory. Actually, LZ sort of does a bit more than that. And then we're going after this with this experiment. But that's just a sort of to get our foot in the door, if you like, and actually understand what we could do with these systems. Like if you take that same bead and you pop it in a Paul trap, or you get arrays of them together, you can start doing all kinds of funky stuff with wave-like dark matter and things like that as well. I'll skip over that. This is just some projections. Hopefully, we'll have a paper out in a couple of months when we've actually run the experiment. And this is just from 11 days of running. So now we've gone from 10 years, 100 million, big infrastructure, run it for years. Have we got WIMPs or not? And at the same time, we've got these types of experiments popping up, which took a year to assemble, postdoc ran it for a month, and did we see anything or not? So okay, we'll skip this. Except say directionality. So the directionality here is what's really cool. If we have directionality, remember that neutrino floor that's going to limit things like XLZD. The atmospheric neutrinos and the diffuse supernova neutrinos, if you had directionality, what I mean by that is that LZ or any of these xenon detectors, if they see a dark matter particle, they just ping, right? Saw something. Directional detector says, saw something, and it came from over there. Because typically they will be very, very low pressure gas detectors. And when the recall, when a particle comes in, it will give a recall, and that track that it produces, you can maintain that track. It's in such a low pressure environment that you can sort of see the track either optically, or you can drift the charge from the track and maintain its structure and say, okay, I've got a 2 millimeter thing pointing that way. It means the dark matter was over there and hit it from this way. And so that's really, really good because you can do away with all your backgrounds with that. Because then you don't care what your backgrounds are doing, right? Because my directional signal, my daily modulation is going to be a much cleaner signal. And that was it. All right. So what was I saying here? Oh, that was it. So very last slide. And here I just wanted to make the point that it could be that we learn very little from direct experiments, right? And so I'm very keen that Accelerator, of course, I keep my eye on. Half of our group at UCL are involved in the LHC and accelerator physics. But then there's cosmology and astronomy and what's happening out there. And could it be that actually the next big real insights are going to come from, the motion, what's actually happening here? How many dwarf satellites are we actually seeing around this galaxy? Is it hot, dark matter? Is it warm? Is it cold, etc., etc.? Answers could come actually from just looking out there again, right? So I'm quite excited about that, especially since it's not guaranteed that you get anything from any of these other experiments. We might be completely wrong. It may not be dark matter at all. The extra dimensional stuff could be, there's so many fun things you can cook up, which is what this picture's about. And this is to say, maybe we just need to, think a bit differently. And the reason I give this picture is because, Feynman spoke about this, right? Feynman spoke about the nature of how we were doing quantum field theory and things like that, right? Is that we've got part of our brain that's very good at objectifying, separating, and looking at particles, and another hemisphere of the brain that's very good at context, space, and all of that kind of jazz. And oh, look, we've got wave-particle duality. Have we? Or have we got a split brain with a corpus callosum in between them? What does that mean for space-time and particles, or, et cetera, et cetera? And you can see this kind of running as a theme right the way through physics, but also geopolitics and everything else, right? This is how you get othering, you get all that kind of stuff going on as well. So you get climate change as well, but I won't bang on about that again. So it could be that we actually are on the cusp of starting to think about things a bit differently, right? If we don't see much new physics from accelerators, from direct detection, from et cetera, what do we do next? And I think it could be, actually trying to understand general relativity and quantum mechanics a bit better here. And the reason I say that is because there's a bit of a, I'm going to tell you an insider hack trick, something I shouldn't admit in public probably, but I do all the time. And that is this: when we think about dark matter, we say dark matter particle, it's a matter. And then we're going to build a detector, we're going to build an accelerator, we're going to go and find this. Why do we think that will work? I think we think that will work is because we've done it in the past. We said, oh, all right, so there should be this tau, or there should be this particle, there should be or the Higgs boson. Let's build this thing, and boom, you find it. But none of those involve gravity, right? It's nothing to do with gravity. I saw QFT in QFT land doing QFT stuff, which is all well and good. Here, what is the dark matter gig, right? It starts with, oh, there's some weird gravitational stuff happening over there. What is that? Let's go to QFT and look for the particle. But we don't actually know how they work together. Am I making some sense? Yeah. So it's just it's something that niggles at the back of my mind. But maybe it's completely wrong and it means, we're all fine and we'll just find dark matter, but maybe we won't. Anyway, I'll stop there. Been rambling a long time. Yeah.
If you were given an infinite amount of money and an infinite amount of infrastructure, is there any way that you could beat the neutrino floor?
Yeah. You can basically start. So your sensitivity will come down like this, and then it will hit the neutrino floor. But then if you get larger and larger and larger, like if your detector is just, so as I move this way, imagine you're building a larger and larger and larger detector. So now it just becomes the background, and then off you go again. So basically you can characterize the neutrino floor and then go. Treat it as a new background essentially, but that would be a astonishingly large detector to get past that. I mean, already 70, 80 tons or so is what we want for XLZD. Barely enough xenon on the planet to try and do that, especially with wars and all that kind of stuff that interrupts a lot of this. It's air separation units that you need to extract the xenon. But even if you had, about $1 million plus per ton, this is expensive. So you need that infinite amount of money. But yeah, in principle, yes. Or you could go direction. You could build a Jupiter-sized gaseous directional detector, right? Or something like that. Yeah, if we need to, we probably will get past that neutrino floor. But first, we just need to see something, right? There's no little motivation yet.